we've got this sphere, and it says that it rolls down, excuse me, down the hill here to B. And the first question is just which one of these graphs here explaining energy is correct. So let's look at Angela's. Angela says up at A that it's got this KR stands for rotational kinetic energy, and the KT stands for translational kinetic energy. In other words, kinetic energy in a straight line. And then that's gravitational potential energy. So Angela says it's all gravitational potential energy up here at A when it starts from rest. And when it gets down to B, she's got it all as rotational. Well, that's not right, because we know that it's moving to the side as well. So it can't just be spinning, which is what this would indicate. And Blake's got the opposite problem. He's got it right that it's all gravitational potential in the beginning, but he says it's all translational energy down at B. So it says that it rolls. So we know that some of that energy's got to be in the rolling form of it here. And if you look at Carlos says, well, some of it's rotational and some of it is translational. And so that is correct in that regards. All gravitational potential down to some rotational and some translational. Now, how do you know to make one less than the other? Well, they told us that the rotational inertia is for this object is 2/5 mr squared. So let's say when we get to the bottom, we've got translational energy, and that's 1/2 mv squared, and we've got this new rotational kinetic energy, and that's 1/2 I angular velocity squared. So let's compare these if we plug these in. They gave us the I, it's right there. So this will become 1/2, the I will be 2/5 mr squared. And what about this angular velocity here, this omega? Well, if you remember from earlier in the chapter, we have a way to find this old school velocity by taking our angular velocity and multiplying by the radius. So if I rewrite that, the angular velocity is the old velocity divided by the radius. So if I square this angular velocity, I'm actually squaring the regular velocity and the radius. So that's what I'm going to do. Right here for this angular velocity, I'm going to plug in this, and so we get v squared over r squared. This r squared cancels with that r squared. And if I am comparing this one to this one, we can each see that they have a half, they each have a mass, they each have a v squared. So this rotational one's got this 2/5. So it's got to be 2/5 of whatever the translational energy is by definition. And if you look here, you probably didn't even notice, but the rotational one is 2 squares tall, the rotational one is 2 squares tall, and the translational one is 5 squares tall. And that's dependent upon the moment of inertia of the system. So here they say, how would each of the bar charts be different if Earth was not included in the system? Well, in that case, then, we could never talk about this gravitational potential energy. That only works when we have it in an Earth object system. So instead of thinking about it as gravitational potential energy, we would just think of it as some outside force doing work on the object, the outside force being gravity. But that's just basically what gravitational potential energy is telling you how much outside work gravity is going to do. Next, it says the sphere continues to roll along the track without slipping at point C. It leaves the track. At its highest point will be above or below where it was at point A. So let's come back here to the picture and think about it for a second. So it comes up here and it launches off of here at some angle. So when it gets to the top of its path here, here's one thing that is true. It's still going to the side because it launched at an angle. So it will still have some kinetic energy going to the side. It will never fully become gravitational unless we shot it straight up. So by that fact alone, it's not going to get to the same height as A because we launched it to the side. And that would be true even if this thing wasn't rotating. It wouldn't get to the same height. But the fact that it's rotating even adds to that effect. It even compounds it. So because it's still going to have sideways kinetic energy, and because it's going to have rotational kinetic energy, it can't get back to the same height as A. It can't all go back to gravitational potential. So our answer here that we should check is that it would be below point A. And then finally, what if it's on an identical track with no friction, so it won't roll? Is the sphere's maximum height after leaving the track greater than or less than the rough track? So because it's comparing to the one we just did, we won't have any of that rotational kinetic energy. It will all be just translational. So it will go higher than it did before, because some of that energy that was rotational when it went down the track with friction and rolled, it's going to be all in terms of kinetic. It still won't get as high as what it was before, like we just discussed, because it will be going to the side, so it still won't get as high as A, but it will get higher than it did if it was rolling along there.